Good evening to all. Today we are going to talk about interaction of radiation with matter part 1. That is, mostly we are going to talk about Compton scattering. So previous lectures we have been discussing the attenuation of radiation. The understanding of interaction of radiation with matter is very much useful to understand the concept of attenuation. We know that X-rays have wave as well as the particle-like properties. While traveling, X-rays travel as waves. While interacting, it behaves like a particles. We all know that X-ray wavelength is in the order of nanometer. For example, it is around 10 power minus 8 to 10 power minus 9 meter. So X and gamma rays interact with the structures that are similar in size of the X-ray wavelength. So atoms have nanometer size dimensions. So it is around 10 power minus 9 to 10 power minus 9 meter. So the low energy X-rays have probability to interact with the atoms which are similar in size. Moderate energy X-ray has a probability of interacting with the electrons, whereas high energy X-rays have the probability to interact with the nucleus of an atom. So in general, X and gamma rays interact in 5 different ways. That means Compton scattering, photoelectric absorption, pair production, coherent scattering and photodisintegration. This Compton scattering and photoelectric absorptions are very important in diagnostic radiology. Compton scattering and pair production is very important in radiation therapy, both teletherapy and brachytherapy. The role of coherent scattering and photodisintegration is much less in medical applications of radiation. Let us see what is a Compton scattering. Compton scattering is also known as inelastic scattering or non-classical scattering. It is very predominant interactions in X and gamma rays, especially in diagnostic radiology where the energy is greater than 26 kV in soft tissue. It is also present beyond the diagnostic energy range up to 30 million electron volt. That means it has a role in radiation therapy. Let us see what happens in Compton scattering. In Compton scattering, the incident X-ray photon interact with an outer shell electrons of the atom. The outer shell electron is nothing but valence electron for which the binding energy is very less. Let us see one atom here. This is the outer shell electron, valence electron. The incident electron comes here and have the interaction here. It loses partial energy and ejects the electron here. This electron is called Compton electron or RECOIL electron. So when you remove an electron from atom, it is called ionization of atom. So while the electron is ejected, the atom gets ionized. At the same time, the incident photon, X-ray photon, goes in a different direction, that is called a scattered photon with an angle theta with a reduced energy, because the wavelength of a scattered photon is higher than the incident X-ray photon. As the wavelength increases, the energy decreases. So in short, in the case of Compton scattering, Compton electron is produced as well as the scattered X-ray photon is produced. So both energy and momentum must be conserved in the Compton scatter. The energy of the scattered X-ray photon is equal to the difference between the energy of the incident X-rays and the energy of the ejected electron. For example, if you take E0 is the incident X-ray photon energy, it is equal to scattered X-ray photon energy plus the recoil electron energy, or the sum of the recoil electron energy and scattered photon energy must be equal to incident X-ray photon energy to conserve the energy and momentum. Additionally, one can also calculate the energy of the scattered photon which is equal to the incident X-ray energy photon E0 divided by 1 plus E0 divided by M0 C square into 1 minus cos theta. The M0 is the rest mass energy, C is the velocity of light, and theta is the angle of scatter. Let us see what happened to the recoil electron. The recoil electron can go either in forward or sideward. It cannot go beyond 90 degree. That means it can go to from 0, this, or it can go to up to 90 degree. This angle it can go. The recoil electron go from 0 to 0 as well as the 90 degree. It loses its kinetic energy further by ionization and excitation the surrounding atom. Thus, the energy of the ejected electron is absorbed by the nearby site. For example, this is the electron. It undergo further ionization excitation and the energy is absorbed in the nearby site. Let us see the fate of scattered X-ray photon. Scattered X-ray photon has higher wavelength than the incident photon, as we discussed earlier. This is the incident photon, this is a scattered photon. It will have higher wavelength, therefore the energy is lower. It continues in different direction with lesser energy. The theta is the angle of scatter. So it may be directed in all angle from 0 to 180 degree. That means the scattered photon can go from 0 to 180 degree up to here it can go. Scattered photon travels in the medium without interaction or with interaction. If there is an interaction, it may be a Compton scattering, photoelectric absorption, or Rayleigh scattering. The energy of the scattered photon may be estimated from the incident energy and the scattering angle. That means if you know the scattering angle and the incident photon energy, one can calculate the scattered X-ray photon energy by using the previous equation. If the incident photon energy increases, what will happen? Both the electron and scattered photon move towards in the forward direction. For a given scattering angle, the fraction of energy transferred to the scattered photon decreases with increasing incident photon energy. That means if the incident photon energy is higher, majority of the energy is transferred to the electron. For example, you can take for a 60 degree scattering angle, the scattered photon energy is 90% at the 100 kilo electron volt, whereas it is 17% at 5 million electron volt. That means if the energy is 100 kilo electron volt, it takes 90% of the instant photon energy, whereas if the energy is increased to 100 to 5 million electron volt, it is only 17%. It shows that as the energy increases, then the scattered photon energy decreases. Let us see the Compton scatter probability. At low energies, particularly in diagnostic range, where the energy is 15 to 150 kilo electron volt, majority of the incident energy is transferred to the scattered photons. For example, at 80 kilo electron volt, the maximum energy transferred to the photon is 61 kilo electron volt. That means almost 80 to 90%. The scattered photon have higher energies and have high tissue penetrating power. Once the scattered photon arises, the detectors used in diagnostic radiology and nuclear medicine are capable of detecting the scattered radiation. As a result, one may get degradation of image quality. Let us see the Compton scatter probability with the scattering angle. Suppose if the scattering angle increases, what will happen to the Compton scatter probability? When the angle is lower, probably the probability is more towards the high energy, like 140 kilo electron volt. As the angle increases, the probability is more towards the low energy angles. So the diagnostic radiology, this is the range actually we are using around here. So where the probabilities scatter is more towards the low energy X-rays. Let us see the role of angle of scatter. If the photon makes a direct hit on the electron will travel straight forward, that is zero angle, and the scattered photon will be backscattered, that is angle 180 degree. When the scattered photon goes in 180 degree, it is called backscattered radiation. This is similar to what one can come across in a film cassette. Backscattered photon is less energetic than the side scatter photon. In summary, in 180 degree photon deflection, more energy is transferred to the electron and less energy is transferred to the photon. If the photon makes a grazing hit with an electron, the electron will go at 90 degree, that is perpendicular. In this direction, it will go in the perpendicular direction, and the photon will travel in straight forward with the zero angle. It goes like this. Photon will go in this direction and the electron will go in this direction. In this case, what will happen? The photon receives the maximum energy and the electron will get the lesser energy. The maximum energy of the photon is limited to 511 kilo electron volt at 90 degree scatter and 255 kilo electron volt at 180 degree scatter. In summary, greater the angle of scatter, greater the energy and range of recoil electron, greater the loss of energy of scattered photon as wavelength increases. Let us see what is the effect of initial photon energy. Suppose if you take 25 kilo electron volt, it is shared by the backscattered photon will take 22 kilo electron volt, recoil electron will get 3 kilo electron volt. That means the recoil electron get a lesser share. As the energy increases from 25 to 150 kilo electron volt, it is actually 100 kilo electron volt to the backscattered photon and 50 kilo electron volt to the recoil electron. That means the recoil electron takes a higher share of energy when the energy is increases. What it conclude? As the incident photon energy increases, the recoil electron takes a major share of the energy. What is the probability for Compton scattering? The incident photon energy must be greater than the electron binding energy. This is the basic condition. The probability of Compton interaction increases compared to raw lip scattering or photoelectric absorption as photon energy increases. That means as photon energy increases, the probability Compton interaction increases. It is more than the coherent scattering and the photoelectric absorption, which will be discussed later. Compton effect probability is proportional to number of electrons per gram as well as the physical density, that is mass per volume. So in summarize, we can say that Compton scattering probability depends upon number of electrons per gram into density. In the case of element except hydrogen, the number of electrons per gram is constant in tissue for all the elements. Compton scattering per unit mass is nearly independent of atomic number since it involves only the free electrons whose binding energy is negligible. Compton scattering per volume is proportional to density. Absence of neutron in hydrogen doubles its electron density. Therefore, heterogeneous materials have higher probability of Compton scattering. Compton scattering decreases slightly over the photon energy, but however, we can write Compton effect probability is inversely proportional to its energy. That means 1 by E. As the energy increases, Compton effect probability slightly decreases. So Compton attenuation coefficient is denoted by sigma. Compton mass attenuation coefficient denoted by sigma by rho, that is actually divided by density. What is the role of Compton effect in imaging? Compton effect is very important in air, water, soft tissue which are low Z materials. It is almost the same for air, tissue, bone, contrast media and lead. The variation is only around 10%. The reason is it has the same electrons, number of electrons per gram in all the materials. The scattered X-rays provide no useful information. It reduces the image contrast, so it creates radiation hazards in radiography and fluoroscopy. In fluoroscopy, large amount of scatter radiation comes from the patient because the staffs are present during the imaging. It contributes to occupational radiation exposure. To summarize, Compton effect most likely to occur with outer cell electron or with loosely bound electrons. As the X-ray energy increases, there is a chance of increased penetration through tissue without interaction, or the probability is higher than the photoelectric absorption. As the atomic number increases, no visible effect is observed. As mass density increases, there is a proportional increase of Compton effect. I hope you enjoyed the presentation. Kindly subscribe and succeed. We will meet with another topic in the next lecture. Thank you very much.